Welcome back to Teaching Physical World. This is Professor Campo at Bethel University in Northern Indiana. And we are picking up with part 2 of chapter 3. So again, this is chapter 3, part 2. Mass and acceleration. Okay, this is a super important point. The acceleration due to gravity is independent of the mass. Whoa, that was profound. Gravity is gravity. It's the same acceleration regardless of what else is going on, right? So my force, let's say I have a textbook, Introduction to Physical Science, that's a great book, and then I have 2 of them here tied together. Guess what? What is gravity? Well, gravity, so that's the acceleration due to gravity, is force over mass, right? We did force equals mass times acceleration. So gravity is force over mass. Well, I have 2 times the force and 2 times the mass, so those 2's cancel each other out. Gravity is always gravity. Wow, that's cool. Friction. Now friction, on an icy day, we hope there's enough friction, right? That we stop in time. Friction can make things hot. 2 kids are playing and they get a rug burn, and that's friction, right? And it irritates the skin and it creates heat. We can have friction. High schoolers trying to burn out in the parking lot, right? And lay some rubber on the ground. That's friction, all right? It's 2 objects rubbing together. We won't talk about coefficient of friction, but 2 objects, depending on what the materials are, have a coefficient of friction, all right? It's a number that describes how hard they rub against each other, okay? Are we talking about racing tires on concrete where they're pretty slick? Are we talking about big rubber tires, big truck tires on rough concrete? Okay, those are different types of, different coefficients of friction. All right, so friction is some sort of resistance to relative motion that occurs whenever 2 materials are in contact with each other. It doesn't matter what state, so solid, liquids, gases, a matter. There's going to be friction. In some, like there's air resistance, wind burn, your cheeks are all burned from sitting outside for too long in the wind. That's friction. So sometimes we want to increase it, other times we want to reduce it. So oil or lubrication on something reduces that friction. But if it's icy, we want to increase it. There's 2 types or 2 states of friction, maybe. And I explained that 2 objects, depending on what they are, have a unique coefficient of friction. There's static friction. It hasn't moved. There's kinetic friction. Now, what's interesting is static friction is always more than kinetic friction. And there's a point where we're just about to slide, right? We're still static, and you have to push, and then it breaks free, and man, you don't want to stop. You can just keep going, right? Pushing something heavy, as soon as I get that baby moving, I don't want to stop. So kinetic friction is usually less than static. We have coefficients of friction. We use symbols. This is the Greek letter mu. So the coefficient of static friction, coefficient of kinetic friction. So mu sub s and mu sub k. Here are some typical numbers. If I have, let's see, wood on wood, here is 0.58 and 0.40. So again, these are multipliers that say, has to do with the force and how much extra force it will take to get this thing moving. Teflon on steel, so like think of your coated pans, your Teflon pans. Aluminum on steel, aluminum on aluminum. Isn't that interesting? The difference between aluminum on steel and aluminum on aluminum. So Newton's 3rd law, for every action there's an equal and opposite reaction. Whenever an object exerts a force on a second object, it exerts an equal and opposite. So it's this equal and opposite. It's this idea that I'm pushing on the board and the board is pushing back on me. So force, one force on an object is equal and opposite to the other force. So equal and opposite forces. Mass times acceleration of object 1, mass times acceleration of object 2. Equal and opposite. And by that way, that's why we can solve many of these concepts that we're exploring right now, is why my engineers can do things like statics, dynamics, mechanics of solids. That's why we can solve those kind of problems. So jet propulsion falls in this same category. So when a jet engine, when the gases explode out the back end of the engine, it forces the jet the other direction. So it's that equal and opposite. That's how exhaust gases make a jet move forward. Gravity is constant, of course. If you jump from a table, you will accelerate to the earth. Hopefully not too fast, right? In reality, both you and the earth are accelerating. However, the earth is so large, has such a large mass, that you don't exert much force on it. This book and I, if I weren't holding it, it was on the table. This book and I are exerting a force on each other. But we both have relatively small masses. It has less mass than I do. So it's not, I don't feel the pull, okay? The earth has a mass so much bigger than I do that I do feel that pull. Now, of course, our bodies adapt and we don't notice gravity, but if there wasn't gravity, we would certainly notice it. So friction on the tires causes centripetal acceleration. So centripetal is that circular kind of towards the center. The passengers continue straight ahead, but the car is turning. So that is, do you see their bodies leaning in that picture? That's what you feel. Now, I drive a big full-size van, one of those tall ones, and my husband drives a little Saturn, and sometimes when he's driving the big van, I'll say, remember which car you're in, right? Because of the way the vehicle's made, the size, the shape, the center of gravity, if he goes too fast on a curve, I feel it, right? We feel it and it feels uncomfortable. So that's that centripetal acceleration. So it pushes you against the door and you're like, slow down. All right, so gravity is a fundamental force in nature. Now, I would disagree with this statement because it says we do not know what causes gravity. You know what? We do. We know that our universe, our world, everything in it was created by a God that is so amazing. He is omnipotent, he's all powerful, he is omniscient, he is all-knowing, and he knew exactly how to put this world together so that it would be in balance. And we know that gravity was created by God as a force. But God is a God of order. He is a God that wants to pull everything together for us and to guide us and to help us learn about it. Says we can only describe it. I think we can wonder in the majesty of this creation, but it is pretty cool to learn how to describe it and how it really works. So the law of universal gravitation, all right? So that's an important law. It says every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Let's take those words and look at the actual formula. So the force between two objects is big G. Hang on, we'll come back and talk to that. Mass of one object times the mass of the other. Now, sometimes when you're talking about the Earth, you'll see one of these as big M, like a capital M, because that's the mass of the Earth. And they're separated by a radius that is squared. So anytime we square a value, it has a really significant impact. So the distance between two objects is squared, so that's very significant. So what is big G? Big G is this universal gravitational constant. It is a number that was derived by empirical work. People did a bunch of experiments and came up with this value, and it's a standard, nationally, internationally accepted value. So it is very small. I see it's times 10 to the negative 11. So yes, that is very small. It's thought to be valid throughout the universe. Now, as soon as we can make it to Jupiter or Pluto and check that out, we will do that. But at this point, we believe that it is valid throughout the universe. It was measured by, excuse me, Cavendish 70 years after Newton's death. It is not equal to little g, which is gravity. It is a gravitational constant, and it is not a force. So let's look at the units. It's newtons times meters squared over kilograms squared. Well, what is a newton? A newton is kilograms times meters over seconds, okay? So those are different units. Often when we have a constant, when we looked at coefficient of friction, that actually has no units. It's kind of like a percentage probability kind of thing where it's just a relationship. The units on big G have to do with these units. So I have mass, so that's why mass is in the denominator here, mass squared. Radius, that's my meters squared. And then I need to end up with newtons, right? Because that's a force. So that's where the units on big G come from. So here is my, my force. I have a mass and a force, a mass and a force. That distance, that radius between them, and typically you would measure from the center of each object. So if we measured from the center of the earth to the center of me, that would be the radius we're talking about. An interesting thing is that gravity isn't exactly the same all over the earth. And the reason why is this radius. If I was below sea level versus Pikes Peak, that radius changes. Guess what? That changes the force. However, we know that on average, it's 9.8 meters per second squared. Now, you may find that some books use 10 meters per second squared. That's a rounding thing. You may in your class have a situation where you don't use calculators, that part of your pedagogy is that you shouldn't use a calculator, and then 10 makes a great estimate of gravity. However, I'm a fan of using calculators, I'm a fan of using Excel, and I love for somebody to find out what it really is. So we use 9.8, 9.81. Could use some more decimal places if you'd like. So again, here's my force equals big G, mass 1 times mass 2 over the radius squared. Again, here's my Earth, and that radius is the distance. And so you see right here, see how they use a big M? That often means the mass of the Earth. And again, those are accepted values. All right, I'm gonna keep going a little bit. I think it's time to go. So if we were in space and didn't have gravity, we would notice that. So what about buoyancy? So buoyancy has to do with things floating. And we have Archimedes, you know, he ran through town saying, Eureka, Eureka, and figured out what buoyancy meant. An object immersed in fluid experiences a buoyant force, so that's the force of the water or whatever the liquid is pushing on the object, equal to the weight of the volume of fluid displaced. All right, let's draw a picture. I know there'll be a picture, but I want to draw one. So let's say I have some water, right? And I have my little boat. All right, the cute little sailboat. Sail. This bit of volume of water, we'll pretend it's pure water, okay? Kind of comes out of your tap. Now I know that's different from place to place. So this is the amount of the boat that is down in the water. The mass, excuse me, the mass of this water is going to be equal to the buoyancy. Okay, So it's how much does this weigh? So mass, now I'm gonna need to multiply that times acceleration, right? So acceleration's times mass, or maybe I actually weigh it in newtons or pounds. How much is this liquid is going to be equal to the weight of that boat, okay? That's gonna be equal to that. And by the way, liquids and gases are both considered fluids for the sake of this argument. So if you had a gas, now you can have compressed gas that would push back because the volume is compressed, so it's a higher weight for that same volume. So to summarize, the weight of the fluid displaced depends on the density. So what about salt water versus fresh water? Milk versus cream, right? Maybe I have something that's a really dense liquid. Perhaps it's a slime or something that really is some sort of fluid that moves and can absorb energy. And so one floats higher in salt water since one needs to displace less salt water equal to one's weight. Now, I don't know if you've ever noticed on really, really big ships, they actually have tonnage listed on the side of the ship. The lower the ship sits in the water, the higher the tonnage, right? So the more it weighs. So you can actually weigh the ship based on those markings, right? So the people that design the ship and figure it out, okay, if it has, based on the volume, right? So that would be a fairly complex volume problem, based on the hull of the ship. Based on the volume, how much water is displaced, and again, probably it's salt water. Most of those big ships are in salt water. How much is displaced versus how deep it sits in the water, and that tells us the actual weight of the ship. So oil floats on water since oil is less dense. Cream floats on milk since cream is less dense. Ships actually will, submarines can vary their buoyancy based on how much water they pump in or out. So linear momentum. All right, so linear momentum. Now it's interesting, one of the textbooks I teach out of uses a different symbol. So just know you might have learned a different one. This book uses little p. So that's linear momentum. That's mass times velocity. So force, let's write those down. Force is mass times acceleration, right? So force equals mass times acceleration. Linear momentum is mass times velocity. So my initial and final momentum is going to be the same if there's no outside forces, okay? So that's law of conservation of linear momentum. If we can also add them all up, we can say the linear momentum of the system, we add all of those. Now, I could have negative, right? Because I could have velocity heading in a different direction, but I still can add up all those momentums values. So the law of conservation of momentum says it remains the same. Again, the idea of an isolated system, think of a bubble, kind of an imaginary bubble, remains the same if there is no external unbalanced force acting on the system. Linear momentum is conserved as long as there are no external unbalanced forces. It does not change with time. It is not affected by time. What kind of problems do we apply that to? Think about a man or a boy jumping off a canoe. That looks dangerous to me. Onto that rock. There has to be some fancy teenager doing that, I think. When the man jumps out of the boat, he has momentum in one direction, and therefore so does the boat. Because there's nothing external, all right, pretend the water doesn't hit the boat with enough force to make a difference, they're going to end up going in different directions, right? Because it has to have a constant linear momentum. And they cancel out. That means they add to zero. What about this spring? Now, he's going to use a match to separate that spring into two parts, or I'm sorry, the string. There is a spring, but the string The reason why is we don't want to add any external force. We want it to just all of a sudden come apart. So we have two masses at rest on a frictionless surface. When the string breaks and we have a spring that pushes them apart, we're going to have motion, right? And what if we know that the velocity of this first object is 1.8 meters per second squared? Well, guess what? I can calculate the velocity of the second object. I'm sorry, I did not put my camera back where it needs to be. You could not see what I was pointing to. I apologize. So, mass 1, mass 2. So this is before, mass 1, mass 2, velocity 1, velocity 2, okay? My final linear momentum is going to be the same as these other pieces, right? So the final has to be the linear momentum of the two objects. Since we know that that final has to be 0 because it's conserved, they're going to be equal and opposite. Well, what is the initial or the linear momentum of object 1, mass times velocity of 1, is equal and opposite to mass times velocity of 2. And when I solve for that, it becomes basically an algebra problem. I find that the velocity of the bigger object is negative 9.8 meters per second squared. So first of all, I notice it's opposite, it's not equal, it's proportional, right? This object is twice as big as this one. So we see that proportional piece. So jet propulsion follows this same kind of a status. Angular momentum, when we think about traveling in a circle or in some sort of curved path, I have my linear momentum, so L, so this is, sorry, that's, again in another class, like this is linear momentum in my other class. So linear momentum in this class is little p. And this is angular momentum. So angular momentum is mass times velocity times a radius. So the radius is the distance to the center of motion. So most of the time we'll talk about something with a nice constant radius. However, it could be something where the radius changes. So if we have some sort of path like this, well, the radius in this section is going to be fairly large. Whoops, I got to get out further. It's going to be fairly large because it's a nice soft curve. However, over here, the radius is smaller. Okay? So whatever the radius, wherever the center of that curve is, that's the radius we're talking about. And again, it's conserved as long as there's no outside force. So mass times velocity times radius of the first is the mass times velocity times the radius of the second. I'm going to pause here and come back in.